Hi guys, I'm going to cover chapter 2, the end of chapter questions specifically, of Essentials of Microeconomics by Nguyen and Nguyen. This chapter is really just a bit of a math refresher before we move on to the later chapters. So a couple of small things like taking elasticities, solving simultaneous equations, that sort of thing. Not too much heavy economic theory. So question 3, I'm going to leave the first two questions. They're quite mathy rather than kind of economics, and hopefully relatively straightforward. So question 3, demand is given by Q is equal to 100 minus 2p. What is the price elasticity of demand when Q is equal to 20? A reminder, price elasticity of demand is how the quantity demanded varies with a change in price. As you can imagine, depending on the good, a price change may lead to different levels of change in demand. So petrol, for example, a price change may not lead to terribly much change in demand. Think about Britain, right? They've had jumps in oil prices / petrol prices, but demand has probably remained relatively consistent. I don't actually have figures, I'm kind of just speculating there. But I suspect demand has remained relatively consistent. Other goods, this won't be the case. So elasticity is attempting to measure how much the quantity demanded changes following some sort of a price change. Okay, formulas down here. Epsilon is the common notation. I've just put subscript P there to remind us we can have elasticities with respect to different things. Here we just have it with respect to price. Okay. Formula, pretty straightforward. P over Q multiplied by the derivative of Q with respect to P. Nothing too crazy there. I can do the derivation for this if it's helpful, but I figured it would just muddy the waters, so I've left it in its final form, and I won't go through the derivation right now. Tip for this, we want to rearrange so that we have both Q and P as the subject. It just makes things a bit easier. You don't have to, but it's the way I do it, and it's generally what I find works best. So we have Q as the subject. Whoops. Let me pull up my little pen. We have Q as the subject in the question. We can easily rearrange this to have P as the subject, and we get this following equation here. P is equal to 50 minus Q over 2. Okay, so we have kind of both Q in terms of P, and also equivalently P in terms of Q. So what I'm going to do, we're going to look at this left term here, P over Q. I'm going to substitute that numerator of P with this, 50 minus Q on 2. So this whole left term here will purely be in terms of Q. Okay, that's what we're going to go for here. We're going to make our elasticity in terms of Q and Q only. So what we do, we take this numerator, P, substitute for 50 minus Q on 2, and then we divide that whole thing by Q. Okay, that should hopefully be pretty straightforward as well. It becomes following. So the left-hand side is now done, and it's in terms of Q now. So let's do the right-hand term now, dq dp. Note that this is dq dp, not dp dq. So we're going to want to start with Q as the subject, and we're going to want to derive with respect to P. So we have a look at this equation given in the question, derive this with respect to P, find it's a pretty straightforward minus 2. Okay. So we are more or less done now. This obviously isn't in respect to kind of Q directly. It's just ended up as a plain number, and we'll leave it at that, but that's fine. So we have now, basically it's just a simple multiplication. We multiply that P on Q term we found earlier, and then we multiply by minus 2, and you're done, more or less. That's kind of the tricky part of the question. So we have elasticity of quantity demanded with respect to price as minus 100 over Q plus 1. Important to note, elasticity changes with the quantity being demanded at any given time. I won't go into that right now, but it's important to note that elasticity changes depending on quantity demanded. And now just making sure we wrap up the question properly. Price elasticity of demand when Q is equal to 20. Got this from the last slide. You easily substitute Q is equal to 20 in there. We end up with minus 100 over 20. This simplifies to minus 5 plus 1, which is obviously minus 4. Now, comes the tricky part. Textbook has elasticity as 4, and you might think, oh, my answer is wrong. The sort of tricky thing here is elasticity of demand with respect to price is always going to be negative, more or less, except for a few special cases. When we increase prices, we expect demand to fall. That's not a sort of crazy idea. So we kind of know it's going to be negative, and as a result, elasticity is often reported in its absolute value. So in this case, the absolute value of the elasticity of demand with respect to price is 4. And that's how it's reported in the answers. So that's fine. It's a little bit murky, kind of depends on who you're talking to and who you're answering your questions for. Just try and get some clarity around that. But generally speaking, we take the absolute value. And in this case, that's 4. That's the answer that the textbook uses, just to hopefully clear that up a little bit. Cool. Okay. So moving on to question 4 now. We're given a demand and a supply function. Demand being this one, P is equal to 120 minus 2Q. Supply as P is equal to 2Q. Solve these simultaneous equations. Now, the trick for this is there's a couple of different ways of solving simultaneously. You can sort of take a couple of different approaches. But really, when we're solving these demand and supply curves simultaneously, what we're trying to do is find the intersection point, so where the two curves meet. Okay, so let's draw a really crude diagram here. We have our demand curve, we have our supply curve. We're really interested in this point here that I've just circled. This little point here, where they intersect, because where they intersect we have equilibrium, and the quantity demanded is equal to the quantity supplied. Mark that's clear, and a whole bunch of cool things happen at that point. So that's what we're interested in. As a result, at this point, we know that both of these functions must be satisfied. So P is equal to 120 minus 2Q and P is equal to 2Q. Both must be satisfied. So it lets us do this kind of sneaky little trick. We equate P's. Okay, so I have the demand equation, and I have the supply equation, and I can basically say P is equal to 120 minus 2Q from the demand equation, and then also P is equal to 2Q, supply equation. So this little statement must hold as true. And that's sort of the crux of the question. Okay. So yeah, that's the trick for the more simple ones. But we sort of, in a sense, loosely, we say the P's in the two equations are kind of equal. I'm sort of abusing the notation here, but we can then equate the demand equation in terms of Q and the supply equation in terms of Q, and solve from there. Okay, so it's not too tricky once we get to this stage. We can see quantity is equal to 30, so we know for a fact that in this equilibrium, Q is equal to 30. Just remember, you need to solve for all the variables. So we've solved for Q, make sure we solve for P. The way we solve for P is straightforward. We substitute Q is equal to 30 into either equation, and we can see if we substitute Q is equal to 30 into the supply equation, for example, we'll get some level of P, call it P1 here, and we'll get exactly that same level P1 if we substitute Q is equal to 30 into the demand function as well. Okay, so we substitute it into either. Here, I substitute into the demand function, and we get a price of 60. Okay, yeah, I more or less talked about that. I'll skip that for now. But yeah, this is kind of diagrammatically. I pulled this from Desmos. Desmos is a really good tool for graphing curves out, finding intersections, that sort of thing. Main one that I use. The labels, the axes aren't labeled, obviously, but we can kind of just imagine you here, you here. And that's pretty much it. So we know Q is equal to 30, and we know P is equal to 60. when we solve simultaneously, and that's our sort of intersection point there. Okay. Yeah, so that's 4 kind of wrapped up. 5 now, we're given a profit function. So profit commonly denoted with pi. It's in terms of Q. So what this function is it's telling us the firm's profit depending on how many units it produces and sells. Okay, so Q is the number of units produced and sold. The question is asking us to maximize that profit function. I've written a little bit of a general procedure here. The first step is to take the first derivative with respect to Q, set that to 0, solve that equation is step 2. So you find the Q that corresponds to that first derivative being 0. And then lastly, step 3, we just want to check the second derivative as well. We want to make sure we're finding a maximum and not a minimum. Okay, so purely hypothetical, doesn't really make a lot of sense. But imagine we had a profit function and it was convex, as we have here in the second diagram. Okay, the stationary point, so the Q value that sets first derivative to be 0 is actually a minimum in this instance. So we just need to check that second derivative. Okay, hopefully we find a second derivative that is negative, because if that's the case, we're maximizing. If we find a second derivative greater than 0, we may actually be minimizing. Okay, just to be clear, it's very kind of hypothetical / theoretical to have a profit function that looks like this second one here, just because you could constantly increase Q, and you could just make like more and more profit by increasing Q, which is that horizontal axis there, which doesn't make a lot of sense. Okay, pretty easy, pretty straightforward, hopefully. So we take first derivative of this profit function with respect to Q. I'm going to get rid of that because I've made a bit of a mess on that one. Back. Cool. Okay. So take the first derivative with respect to Q. We set that to 0. We end up with this equation here. We solve for Q. Very straightforward. Q is equal to 20. So we just now need to check second derivative now, just to make sure we are indeed maximizing and not minimizing. So we take the second derivative. We end up with -4. It's less than 0, which means our profit function looks something like this, in that it's concave. Okay, yeah, so it's this, and it's not convex. So we know at the stationary point, so when that first derivative is equal to 0, we do in fact have a maximizing value of Q. Okay, so that's kind of really the crux of the question. We've solved. We know that Q is equal to 20, yields the greatest level of profit. Now this is it plugged into Desmos as well, just sort of for proof of the answer. But we can see here the red line is the profit function. Again, I'll try and label this axis, so we'll call that Q, and the vertical axis is our profit function. We can see we get that maximum level of profit at Q is equal to 20. Okay, as we sort of managed to figure out just mathematically before. So that's pretty much it. Yeah, feel free to leave any questions below. If you do have any, I'll try and get back to them pretty quickly. I will try and give chapter 3 a crack, and I'll probably just move sequentially through the textbook. I feel like having worked answers might be useful for some students.